couple of things I wanted to clear up from last time. First of all, there's a little table here. And I forgot about this. We're going to start with this. And the number for steric hindrance from diaxial interactions is 2 kilojoules per mole for chlorine and 7.6 for methane, or methyl, I'm sorry. 4.2 for hydroxyl, but that one can get complicated. We already talked about it. For ethyl, it's 8.0. This would be isopropyl, 9.2. And tert-butyl would be 22.8. Now, in the last video, I kind of started off talking about these conformations and which one would be preferred, the preferred conformation, and how to kind of predict that. And I forgot when I was doing it about this table, so I was mentioning something, oh, I can't do that unless I have the software. And the software is much more accurate than the table. And it's got more than, 6 groups in it. You can test everything, all kinds of interference. But what we could have still made a prediction. So I was starting off talking about this guy there when that was built, and which conformation would be preferred. Well, if chlorine was up, you've got this steric hindrance there. That's a 2.0. Methyl group down this way, I think that's 7.6, so the combination of that would be 9.6. And if we flipped it like so, this would be 0 for steric hindrance up here, and this would be 0 for steric hindrance up here. Now, it is actually more complicated than that, because there's other interferences that come into play, and other interactions that come into play. For instance, is there any, basically electron affinity here? But those numbers give us some guidance, so I forgot about that part when I was talking about this. Another boo-boo I found when I was going through there, I got a little confused at one point, because when I went to D, I skipped D and went straight to E, and then I got confused. Let me show you what I mean. You probably caught this when I was on this one. So I had a methyl group up and a bromine group up, and then flipped it around. So this is not, by the way, on this one here, it is not the same thing as turning this over. If I took this molecule and flipped it over like a pancake, I'd have these two down. And that's a different conformation. It's a different isomer. But it's up and up. So I skipped from D directly to E and got confused in the process for a second. So let's go back to D. If I have bromine up and I rotate that around, call bromine my first one, and methane here, and then I flip this down, and rotate that while I'm at it a little bit, then they both become equatorial, and the one that is preferred would be this one. I'd have steric interference here of 7.6, by the way, for the methyl group. A bromine is not listed on that table, so don't know that one. You can probably look it up online or something, but there's enough there for you to learn how to do it and get the idea. Okay, so going on to, I thought as you read that it was very self-explanatory. And I don't think you're going to have any trouble with that. So let's go directly to the problems. I think you're going to be, if you have a little patience going through that, it's very easy to see. But let me know if you need to see something. I'll go through it. But I'll build the model and I'll show you using the model. But I just really think you're going to have that. So let's go to 4.33. If you find a mistake here, let me know. But this is what I've got for 4.33a. Okay. If I call this my number 1 and this the number 2, then this one's up out of the page. If the cyclohexane was flat, which we've already seen it isn't. It's going to be half chair or boat, probably. And then the this methyl group is down into the page, so we're going to call it the number 2. So if I draw it this way, then this would be up out of the page. There would be a hydrogen here that's equatorial. This would be down. The hydrogen here would be equatorial. If I rotate this around a little bit and flop this down and put this methyl group here, it becomes equatorial, and this CH3 becomes equatorial here. Hydrogen here, hydrogen here. Okay, well, the numbers for this, there's no steric interference for, at least the way we calibrate that. There's no steric interference for these methyl groups up here. So this is null, 0, null. This one's 7.6, this one's 7.6 to interfere down here with stuff. This one's 7.6 here. That total should be 15.2. So the one that is preferred should be the lower energy one here. Okay, and then 4.33B. I'm gonna call that one the number 1. This one the number 2. Flat in the page, they're both up. I've got a methyl group and an isopropyl. So if I put the methyl at the number 1 position and up, there's a hydrogen. And then in the number 2 position, hydrogen is down in axial position, so this isopropyl would be up. And this should come out a little farther. This should be a little bigger, maybe. Same here. But that interference is, we're going to say 0 with up here. This methyl group is an interference of 7.6. If we go this way, and this should probably be bigger like so, that interference is 9.2. 9.2 is the larger energy value, so the preferred conformation is going to be this one. Okay, let's go on to C. Again, if you think I've made a mistake, let me know. I'm going to call this one number 1, this one number 2, this one number 3. And this is down into the page, up out of the page. So we'll put my number 1 position on the right, so we'll rotate it around. Here's my methyl group. It's a down. Hydrogen is axial up. The next chlorine is down. Hydrogen is axial in the up position. And then I have a chlorine in the up position and hydrogen in the equatorial. This interference here off the bottom is a 2, and this interference is 2. How do I get these numbers? Well, I guess maybe I assumed you knew that. In this table right here, chlorine is 2 apiece, methyl 7.6. And this is for steric hindrance from 1,3 diaxial interactions. So it has to be in one of the axial positions. This one is not going to be, this is equatorial, for example, when you have this tert-butyl. And it's here it's interfering with everything in the ring, so it's 99.9% of the time it's over here. And by the way, if you look at the numbers over here, it tells you out of 100%, if you want, or out of 100 times, and down to this one. Then this one's 10,000 to 1. It'll tell you basically if you have, well, see, the one that's pictured is this one. If you have 10,000 of this molecule, you should expect 9,999 of them to be like this and 1 to be like that. That's what's going on here. Okay, so that's where I'm getting these numbers. And I forget, I was on C here. Okay, down, down, up. Okay, so methyl down, chlorine down, chlorine up. So there's a 2 and a 2 interfering to give you 4. If I push the methyl group this end of the molecule down into the other chair conformation, then the interference between this methyl and all the stuff down here is 7.6. That's less than 2 plus 2 equals 4. So this has more energy interference, more energy to, I don't know how to say that. Anyhow, this is the preferred less steric interference method or conformation. Okay, then on this one, I'm going to call this number 1, 2, 3, and 4, into the page, out of the page, into the page. Okay, so into the page for methyl group number 1. There's my axial hydrogen. Chlorine, into the page, equatorial hydrogen. Number 3 was up out of the page, the hydrogen is equatorial. Number 4 is into the page, it was down, hydrogen was equatorial. So I have a 2 interference here, and a 2 interference there, and a 2 there. That one's a 0. So it's 6 total here. Here the chlorine are all equatorial, but this one interferes at 7.6. So this is the greater amount. The preferred conformation is the one with less total interference. Now those numbers on the table are going to give us an approximation that's pretty good in limited circumstances. You really, in order to get the actual numbers on these, would have to run software. E, I'm going to call this one number 1, number 2, number 3. If you order these differently or do it a different way, you can get the same correct answers that look different on paper. So just because I'm doing it this way doesn't mean it's the only way to do it. Into the page, out of the page, out of the page. Okay, so the first one was the lower, hydrogen in the axial position, and then out of the page, hydrogen was in the axial position here, so this was up. And then on the next one, which letter is this? E? I feel like I did this one wrong. I think this one should be, I think I made a mistake. I think this one should be up, and the hydrogen should be axial, and this should be out of the page. Okay, so the interference here would be, what is that, 22.8? Okay, so this one's probably wrong. Because when I go around here, and that goes down, we're going to have hydrogen down, and this way here, and that's going to be 0. So this one would be 7.6, and this one would be 7.6, and that total is 15.2. So this is the greater interference, which means that this one is the preferred. I think that's what I got. Down, up, up. Yeah, I had that one wrong, I think. All right, let's take a look at F. So both of those were out of the page. So if I make this my number 1 and this is my number 3, hydrogen is equatorial. Here, hydrogen is equatorial, both up. That combined interference is 45.6 here, I think, because it's 22.8 plus 22.8. And here it's roughly 0. So the preferred by far is this one. Now, which is similar to what's going on 43.5. Okay, 4.34. In problem 4.32, you drew the chair conformations of lindane, and you have to predict the difference between them, if any. Where did that go? Let's see, that was back here. Let me go back one. Oops, where is it? Bunch of chlorines on there. I may have to go back and do that one by hand. Okay, we're out of time on this one. I'll pick it up on the next one. I gotta find it.